So what I want to talk about is kind of quantum embedding with long-range interactions. So really looking towards ab initio, material-specific description of the electronic structure of equilibrium systems. So this was stuff that was done with two postdocs that have sadly left now, Charlie Scott and Max Nussbigel. So let's go right back to if I can change slides, there we go. Let's go back to a kind of very, very high level overview of what we're trying to do before we get into too many technical details. So let's think about quantum embedding. In this case, I've got a molecule here that's too large for me to solve the electronic structure at my desired level of theory, whatever that may be. So what we want to do in quantum embedding is we want to exploit the locality of the correlations that there are in this system in order to fragment the system into a number of distinct functional subunits. And then the idea of quantum embedding is to be able to say I can solve for the electronic structure of those functional subunits independently and then somehow stitch together back my description of the electronic structure of the whole system. But what we want to do in quantum embedding, which makes it distinct from many other forms of embedding where you exploit locality of interactions, is that each of these fragments want to be open quantum systems. And we want to take into account the true quantum fluctuations that stabilize these fragments, and then they involve charge fluctuations, spin fluctuations, and in more general terms, kind of entanglement between these subunits and the environment. And so one way to put the kind of challenge of quantum embedding is to ask, how do we describe those quantum fluctuations and approximate them into a suitable auxiliary small enough for us to then solve at a high level of accuracy. Okay, so this is where we want to start from. And just to lay the scene, I want to kind of compare and contrast two different approaches to this idea of quantum embedding. The first is probably much more familiar to many in the audience, which will be this dynamical perspective. And that, gives rise to methods like dynamical mean field theory and many related approaches. So the idea there then is that we are kind of based on the idea of Lovedean partitioning. So we can think about starting from just a simple one-body picture, and that we take our Hamiltonian and we split it up into a system block and an environment block. And similarly, we can split up the eigenvectors in this way. And many of you will have seen that, a few lines of simple linear algebra can downfold the effect of the environment block of that Hamiltonian into a new nonlinear effective Schrödinger equation that just solves for the system component of the eigenvectors and the associated eigenenergies. But what you get to affect this kind of reduction in the dimensionality of your problem is that you end up with this kind of energy-dependent potential that you have to describe, right? That's your generalized self-energy or your hybridization function, which has this resolvent operator here, which couples your system block to the effect of the environment. And so DMFT and related approaches think about this energy-dependent hybridization or coupling to the environment. And if we can describe it exactly, then that means that you conserve some kind of one-body Green's function or propagator over your fragment, your system fragment. And then, of course, we can include interactions in this auxiliary model, and we can perform some self-consistency. And then if we want, we can also generalize this to a two-body embedding, or indeed, when our original problem is described at a correlated level of theory. However, in recent years, I think there's been a fair bit of work in describing projection-based approaches to quantum embedding as well. So I'll briefly sort of contrast the two different kind of paradigms. Projection-based approaches ask a slightly different question. They ask the question, if I want to describe my fragment that I've cut out at a given level of theory and with a particular observable, what is the space of states in the environment that I would need to couple to in order to describe that observable over my fragment at a given level of theory. So this is asking essentially what is the space of those fluctuations into the environment to reproduce a given expectation value. And this is very related to the idea of things like Schmidt decompositions from, let's say, matrix product states or DMRG. The idea that you have a correlated state over an entire system, you know, pull out, let's say, a single degree of freedom. That's an open quantum fragment, and you can perform a Schmidt decomposition, and that isolates then a number of states in the environment, the minimal number of states in the environment that you need in order to describe the coupling of that open fragment to the environment at a given level of theory. So in DMRG or something like that, then that would be the kind of n-body density matrix that you're conserving over the fragment. However, in 2012, in this paper here, the idea was to say, okay, can we think about a quantum embedding approach now, that instead of looking at the eigenvectors of the n-body density matrix, let's think about the eigenvectors of the environmental part of the one-body density matrix. And then if we're just thinking about a one-body density matrix and the original level of theory is simply a mean field level of theory, then what we're doing is we're exposing a number of single particle degrees of freedom in the environment that we have to couple to in order to conserve a mean field one-body density matrix. Now, you can think of this as a one-body density matrix as the instantaneous part of the local Green's function, right? So that's the observable that we're conserving if we can couple to these external degrees of freedom. It's a very general framework, and you can actually extend it to other properties as well. You can extend it, for example, to spectral moments in order to conserve higher energy expectation values over the fragments. And actually, in that way, you can rigorously connect this approach. You can have a hierarchy of Barth states which directly extends all the way and straddles these two perspectives. So you can get back to DMFT from this density matrix embedding theory perspective by increasing this Barth size. One thing that I will stress throughout this talk is that these Barth orbitals are physical degrees of freedom. They are orbitals that can be expressed in the environment. So one interesting thing that allows for, in contrast to the very kind of fictitious nature of the Barth space in DMFT, is that we can project the interacting Hamiltonian into those Barth degrees of freedom. And so that includes a portion of the screening that you would want for the interactions in the fragment. Now, we'll come on to lots of caveats about what that actually means in practice later on in the talk, but I think it's important to acknowledge that these Barth orbitals are physical. Okay, so our focus today, as I said, is going to be thinking about realistic long-range Coulomb interactions and the challenges that that has intrinsically for an approach where we're essentially truncating to small local clusters. And we want to do this without empiricism and allowing systematic improvability in our results. And there are lots of different cases where the nature of these long-range interactions and how that couples to strong local degrees of freedom gives rise to a whole host of interesting emergent physics, right? From plasmons to how heterogeneous catalysis works, and Kondo physics, of course. So first of all, we'll present kind of our approach to this projection-based single particle embedding. We'll think about an extension to two-particle embedding, where we can directly get the physics of long-range coherent excitations which are coupled to a local region. And then we'll finish off by thinking about how we can approximate this and give a new approach to thinking about developing statically screened effective interactions. Okay, so first of all, our approach to ab initio quantum embedding in this projection-based approach. So we first of all need to build up this single particle cluster, and we start off by taking a fragment or an impurity degree of freedom, right? So if we're dealing with ab initio systems, I'm assuming in the rest of this talk that our fragments or our impurities, if you want to use that terminology, just consist of the valence atomic orbitals on each atom, right? Then what we want to do is we want to couple that, first of all, to the density matrix embedding theory Barth, right? So this is the Barth space that will reproduce the one-body mean field density matrix over the fragment space. And due to the property of the Schmidt decomposition, the number of Barth orbitals required to reproduce this instantaneous part of the local Green function has to be at most the same size as the number of degrees of freedom on each fragment. And you can see here as an example, we take the 2s and the 2p atomic orbitals on a graphene sheet, and here are the corresponding bath orbitals at the mean field level that they produced. And you can see if you sort of take linear combinations of those, they will produce the kind of bonding and anti-bonding orbitals that give rise to sp2 hybridized carbons in graphene. So that is plausibly the space needed to reproduce the local mean field density matrix. But we need to be able to systematically go beyond this, right? This is taking the bath orbitals to reproduce the mean field density matrix. It doesn't take into account the interacting physics, which is ultimately what we want to converge in these quantum embedding methods. So how do we systematically expand this single particle cluster? Well, what we can do is we can say, instead of saying I want to reproduce the expectation values of the single particle density matrix from a mean field level of theory, what I want to do is take them from some correlated level of theory. And the simplest one that we can start with is just to think about the second order bare perturbation theory diagrams, which would describe the quantum fluctuations at that level from the fragment into the environment, right? So we can consider those local diagrams, and we can construct again a bath space in order to reproduce those fluctuations. Now, it doesn't quite reproduce those fluctuations, because what we do is we still take the correlated contributions to the one-body density matrix. So ultimately, we're still decomposing a one-body density matrix. It's just coming from a correlated level of theory. And because of that, it means that we don't have these rigorous properties of the Schmidt decomposition, which truncate the number of orbitals that this gives rise to. This is actually a feature, not a bug. It gives us a systematically improvable parameter whereby we can choose the size of this bath natural orbital basis. And by truncating that, we can get a systematically enlargeable auxiliary model or cluster space that we can converge in principle to exactness. And this is related to a number of ideas that go back to ideas of local quantum chemistry by a number of people going way back to the 70s. So here's an example here, again in graphene. If we take one carbon atom, this is now the density of orbitals in this cluster as we increase this truncation, and it captures the higher energy and longer range quantum fluctuations required to reproduce the correlated one-body density matrix. We can then do our high-level correlated calculation in this space and iterate appropriately. So this can all be done in an n-cubed time over the full system in order to construct this quantum cluster for each of these different fragments. And again, just to stress that these bath states, including these bath natural orbitals, are physical degrees of freedom that live in the environment, that are designed to reproduce the correlated contribution to the one-body density matrix. And we can project the interacting Hamiltonian into them prior to solving with our correlated method. And so it does get a portion of the screening and the long-range interactions and the way that these screen the fragment, because these are all interacting bath spaces. Okay. This isn't really going to be a methods talk, but I will flash up some results just to sorry, yes, it's not really going to be a results talk, but I will flash some up just to validate what we're doing here. So this is diamond, fully ab initio. What we're doing is we're fragmenting everything into atoms, and we're looking at the convergence here of the supercell size for different size truncations of these interacting bath spaces. And what you can see is that the size of these interacting clusters saturates for a given threshold of these bath spaces. So we can increase the supercell size, and the resulting size of the, let's say, impurity models, although they're not really impurity models anymore, it saturates. So it's capturing the interacting physics at a given length scale. And you can see again, if we look at the energy of the system, then as we tighten this threshold, it converges quite monotonically. down. And by doing that at different lattice constants, we can sketch out equations of state, rigorously converge them, and indeed structural parameters. And we get results which are well inside the scatter of different exchange correlation functionals and in very, very good agreement with experiment. We can do this for sort of longer range interacting systems like graphene. Again, we can't maybe fully converge with respect to this Barth truncation threshold, but once again, we're sort of inside experimental uncertainty in terms of the equilibrium lattice constant here, and again, inside the scatter of different exchange correlation functionals. And we can really converge with respect to the K-point mesh. Can go to slightly stronger correlation, strontium titanate, and we can look at things like the occupation of different atomic orbitals in the T2G and the EG sets, and compare them to kind of literature values within LDA plus U frameworks, and also, again, converge equations of state. Finally, one little application of this kind of base quantum embedding that I wanted to present to start with before we go on to the extensions is looking at the absorption of NO2 on graphene, which has been quite an interesting system, and they're looking at using graphene as kind of pollution sensors. But when they come to the theoretical modeling, what they wanted to understand was how an electron transfers from the NO2 onto the graphene sheet as a function of the gate voltage that's applied to the graphene sheet. And of course, all sorts of different density functional approximations lead to a smooth transfer of charge from the NO2 onto the graphene sheet due to essentially self-interaction error and the overstabilization of delocalized electronic structure. But what we find is that by taking these fragments to be the NO2 absorbate and the graphene sheet, at a given gate voltage, we get a much more physical, discrete unit charge transfer from the NO2 onto the graphene sheet. And that was quite, that kind of agreed with some experimental findings. But I want to talk about the methodology really today and ask, what are we missing in this embedding approach? We have to go to really quite large interacting Barth sizes in order to converge to the correct physics. And is this really the most efficient expansion? Is there something we can do to improve it? So one thing we should be clear is that the Barth states are all constructed from the decomposition of single particle variables. That's what we're trying to conserve over our fragment spaces. Now, these single particle variables may be from correlated levels of theory, but we're still doing essentially a Schmidt decomposition of single particle variables. So we're trying to conserve the single particle density matrix over the fragment. So that means that this isn't really an expansion in terms of the interacting space that we want to describe for these quantum fluctuations between the fragment and the environment. So we're not able to describe in this local framework something like genuine long-range coherent many-body excitations, things like plasmons, things like dispersion-bound systems, and they're going to be really critical to think about longer term. And what I'm going to talk about next, really, if you're comfortable with the idea of going from DMFT to extended DMFT, which is a two-particle self-consistent extension of DMFT, then we can think about the same thing here. How do we go from DMET, where we're constructing, algebraically constructing Barth spaces in order to conserve one-body descriptions, observables of fragments? Can we go to now a two-body analog of this process? So this is going to be a really, simplified cartoon description of the physics we want to capture, which is probably way too low level for or high level for this specialized audience, but we'll do it nonetheless. When we construct our single particle local cluster and we do our correlated calculation within them, essentially what we're doing is we've had to truncate the range of the interactions within this small fragment. And so what we're missing is the correlated beyond mean field interactions with all the other electrons in the system. And those, of course, will have charge density fluctuations across the length of this system of interest that's many-body and will lead to a back reaction on the electrons in the cluster, and they will serve to reduce the effective interactions within the cluster. And this is exactly what we mean by retarded interactions within a quantum cluster. And really often the kind of dominant physics that we want to describe is the particle hole random phase approximation fluctuations. These are essentially the charge density fluctuations driven by the polarizability of the environment, and they really can be the dominant correlated contribution for small gap polarizable systems. Think high density limit of the uniform electron gas. And they're absolutely crucial if we want to get a lot of the correct kind of physics in an ab initio perspective. So we want to include these this coupling of local strong correlation to these long-range coherent density fluctuations, which can't be decomposed into a strictly local single particle degree of freedom that we can use as a bath. So that's what we want to do, formulate a rigorous bath space for coupling of these local fragments to these long-range coherent fluctuations. So we want to think now in the same framework of this projective embedding kind of paradigm, which is to say, okay, can we think of an expectation value, an observable that is local, that we want to conserve at this given level of theory, RPA, such that if we were to do RPA on the resulting reduced dimensionality cluster space, it would by construction be the same as if we were to take the full system RPA solution. So these observables that we want to conserve in our cluster model are the two-body correlation functions corresponding to the instantaneous part of the density response function, the dynamical density response function at the level of RPA. So we can conserve actually not just the fully instantaneous part, but actually the first moment of the density response, the reducible density response function at the RPA level as well. So what we want to do, what we can do is we can sort of recast the RPA to look a little bit like a mean field theory, in which case we can then kind of reuse everything analogous to how bath spaces are constructed in the original density matrix embedding theory. So in the RPA, for people that aren't familiar with it, I kind of think about it maybe slightly differently to how kind of more traditional condensed matter theorists think about it. But what you do is you assume that particle hole fluctuations obey quasi-bosonic-like statistics, right? So to first order, we can think of particle hole excitations as obeying this kind of bosonic-like commutation relation. And then that's fine as long as you don't look at these quasi-particles too carefully and realize that they have internal fermionic structure. And then the RPA is essentially a mean field theory of these quasi-bosons. And so what you can do then is you can construct an equation of motion, Hamiltonian, which is a little bit like a Fock matrix, but instead of single particle degrees of freedom, you have these particle hole excitations, which then, to make the theory tractable, we rewrite in terms of these effective quasi-boson operators. And then if you work it through, you can end up with an equation like this that's, that crops up in many different equation of motion formulations. That is the Casida equation. And it looks a little bit like a Hartree-Fock-Bogoliubov theory in terms of these bosonic degrees of freedom. Once we have a kind of a mean field-like theory, we can do the Schmidt decomposition entirely analogous to the single particle case that was used in density matrix embedding theory. So I'm not going to go through all of the maths. I don't think that'll be instructive, but what we end up with is we end up with our fragment coupled to the original fermionic bath, which captures the one-body reduced density matrix at the mean field level. And then it's coupled to a small number of additional bosonic degrees of freedom, which describe the which described the long-range RPA coherent interacting physics in order to make sure that the two-body density matrix, or the instantaneous part of the density response function, is conserved over this cluster. So we have a way to construct, without any numerical optimization, a finite set of algebraic Barth bosons. And if you were to integrate those bosons out, they would provide the effective dynamical long-range screening of your fragment space. It's exact in an RPA in RPA sense for the two-body density matrix by construction, and the number of bosons is strictly finite and independent of system size. And that is, again, just coming from a property of the Schmidt decomposition. The other nice thing, which I'm not going to go into talk about detail, is that we have a way to do analytic self-consistency in the two-particle interaction kernel of the underlying RPA. So we can do this all self-consistently and exactly take out the two-body density matrix that we get from our correlated level of theory and put it back into an effective interaction, which is self-consistently optimized over the entire system in order to get these instantaneous parts of the density response to match at convergence. Okay, so this is an example of what you would get if you took a few low energy degrees of freedom from a benzene molecule here. You get a certain number of bosons that couple that have very specific energies given by these vertical lines. And if we were to integrate them out, we get an effective dynamical Coulomb interaction that's given the real part and the imaginary part by these blue and orange lines respectively. And as we go to high energies, the real part of this screened Coulomb interaction, as expected, goes back to the bare interaction limit. So we can test this on really just a small step from the Hubbard model. We go to the nearest neighbor interacting Hubbard model. So that means that then whenever we take a cluster of sites, we're necessarily cutting through one of the important interactions that we need to describe, and these need to be recovered by this bosonic Barth description. And if we do that, we do a two-site fragment embedding, U equals 6T. We've got a cluster of 4 fermions, so that's 2 from the embedding fragment, 2 from the fermionic Barth, and then we have a maximum of 8 bosonic degrees of freedom rigorously in the cluster in order to get the screening for the static observables. And we can do this with full self-consistency, and then if we take a cut through V, we have this phase transition between the spin density wave and the charge density wave, and we get a coexistence for this region here, but this is the result from very accurate results on where that phase transition should be, and this green line here is dynamical is DMRG calculations, and again we get this phase transition in pretty much the right place, so we're quite happy, and we can scan out the whole phase diagram. We can also get dynamical results as well by going to the underlying self-consistently optimized RPA description of things like spin and charge dynamical correlation functions. And once again, if we compare to dynamical DMRG, we get roughly a similar sort of description of the spin and charge channels that we observe, and this is a value of U and V, which is roughly equivalent to strontium cuprate. And just by way of comparison, if we were to do the just simple RPA on the full system, or indeed do a purely fermionic embedding without any of the bosons to provide the long-range screening, and coupling to these long-range coherent excitations, then you find you don't get anything like the correct results here. The other thing that's quite nice is we can look at the self-consistent effective static interaction across the entire system that results from matching of these local correlation, two-body correlation functions that takes place in this quantum embedding, and you can see the change in the interaction strength at different length scales. It goes from being a very local interaction, having a much longer range, and indeed you see some components of this interaction strength becoming negative, so it's an attractive, effective interaction. And that will be certainly interesting to look at in the context of superconductivity going forwards. But I want to finish by talking a little bit about going to a purely static and purely fermionic auxiliary model in order to do this quantum embedding. Ultimately, mapping down to an auxiliary model that has both coupled fermions and bosons is useful. It's the only, it's how we can get some dynamical interactions, but it's expensive. We have to then work with coupled fermion boson solvers, which we're in the process of making sure we've got the infrastructure to do, but it's not ideal. So how can you do this? And this is also related to the question of what's the right effective static interactions in a general sort of quantum embedding method. So one of the most widely used methods, but not by any means the only one, is to think about using constrained RPA, right? This is where you have your bare interactions V here, and then you couple them to the polarizability in the external environment, which contains all of your particle hole diagrams. And then if you have an infinite series of these, then you can renormalize to any order of effective interaction with the environment within this particular channel, which is normally taken from the particle hole RPA. This has a lot of really nice properties associated with it. This gives you a renormalized interaction that's renormalized by these polarization bubbles to all order. And it means that if you could use this effective interaction in your model space, it would exactly reproduce the dynamical density response of the full system projected into that subspace. But it does have quite a few deficiencies as well in terms of a practical method that can be used in general. Often people will want to have a static interaction, and so they will have to take the static limit of this effective interaction, which can be, in general, quite uncontrolled. So normally they'll take omega equals 0, but in which case it will formally remove these nice properties that we have above. The other sort of, I think, maybe the larger sort of technical difficulty in the application of CRPA is that this internal space that's defined to be the space that is disjoint to the external space where the screening is applied, it must be a band description, right? So you must select the bands in which you want to downfold into. And that's problematic if the aim is to not downfold to a long-range interacting low-energy model, but instead a local model that we want to use for quantum embedding. Because in that case, we then need to truncate the range of the interactions, and they can be very significant if your fragment or your impurity has strong hybridization with the environment. And then it will miss a lot of long-range intra-band screening that can be important. And another point is that these interactions can actually change the underlying band structure of your model. So there are some, technical difficulties. So I want to sort of maybe try and propose an alternative that we've kind of recently been investigating. And again, ask this question from this idea of some kind of projective quantum embedding framework. Can we think about conserving a physical observable over some local subspace, and then think about what is the right static interactions that we can have in that subspace in order to conserve that expectation value over the full system at a given level of theory, in this case, RPA. So this is where it might get a little bit technical. Again, we want to think about the interaction-driven part of the two-body density matrix, which again you can think of as simply just the instantaneous part of the dynamical density response. Now we can write this in RPA theory in this very simple compact form here, where you've got x and y here, and x and y are just the eigenvectors that come out of the Casida equation here, this equation of motion for these quasi-bosons over the full system. So where does the interaction actually enter in these Casida equations? Well, the interaction enters in these A blocks. The B blocks are independent of the interaction. They just depend on the irreducible polarizability. But the A blocks have the bare interaction here plus the excitations at the reference level of theory. So once we have this equation and this bare interaction cropping up here, because the bare interaction only enters linearly in this formulation, you can actually formally invert this process. So what we can do is we can take a density, a two-body density matrix essentially over the full system, which we can compute at RPA, project it into a local region of interest, and then invert these equations in order to find the interaction that would give rise to the instantaneous part of the density response in the subspace we desire. Okay, this is the equation that you have to do in order to get it. It's not very difficult and can be done then in one line. The complicated stuff is getting it down to be n cubed or n to the 4 scaling in terms of the size of the full system, and we can do that as well. But you know, if you want to think about it simply, it can just be implemented with this one equation, and that gives you a screened interaction space, which will exactly and by construction reproduce the full system instantaneous part of the density response at the level of RPA projected into that subspace of interest. Okay, so this has a few nice properties. If we take this as our screened interaction and then do further correlated calculations, it directly reproduces the screening of physical observables. So this isn't about finding some screened Coulomb interaction, which is ultimately a fictitious object. This is about directly reproducing a physical observable. And indeed, it will reproduce things like the subspace energy at the level of RPA, which can be directly computed from the instantaneous part of the density response. It doesn't require you to downfold directly into a band picture. You can apply this and downfold directly to a local cluster model. So it won't mean you'd have to truncate the long range affected interactions if you then want to subsequently use these interactions within a quantum embedding. There are some caveats to this. I will discuss later if interested, but it's a much looser condition in terms of the space that you can screen these interactions. It will also reproduce.
Georgie, if you want to keep time for discussion and questions, you should conclude in about 2 minutes or so.
Okay, I'll do that. It will reproduce the first 2 moments of the GW spectrum. 2 interesting features is that it only screens the particle hole interaction channel. It doesn't screen all channels of the interaction. And as I said, it's static by construction. So I think I've just got 2 slides of results I'll go through. This is again is the example of benzene downfolding into a low energy subspace. This is the dynamical effective interaction from the RPA. If you take the static limit, you just get this. If you take this mRPA effective interaction, it's somewhat less screened than just taking the static limit, because all it's trying to do is reproduce just the low energy. It's only trying to reproduce the instantaneous part of the density response, not just the low energy limit of the screened interaction. We can also think about the error that it makes in actually the correlated wave function that's computed within that subspace. If you take the bare interactions, then the error of the actual wave function amplitudes, the correlated part of them, is about 35% in error. The CRPA screened interactions give you about a 27% error, but this approach gives you only a 19% error if you want to consider the correlated part of the probability amplitudes compared to the exact ones. And so we can then look across a much sort of more diverse test set of molecules of different sizes. We're doing now quantum embedding, thinking about each atom as a different fragment, doing the standard quantum embedding that I described at the beginning, and we're looking at the errors and the distribution of errors over this large test set, using bare interactions in the embedded subspace compared to the effectively screened interactions. And it leads to a reduction across different sized basis sets of about 2/3. So that's the relaxation in the wave function in this subspace due to the screened interactions. And we can again apply this to something that does support long-range coherent excitations like graphene, where we can see that by increasing the size of the bath space and getting longer range fluctuations, if we use these bare interactions in orange, we actually get a much faster convergence with respect to the local spin or the local charge fluctuations compared to just using the bare interactions. And that's a persistent gap that really persists. Indicating that these bare cluster expansions are very slow and not designed to capture this sort of long-range coherent physics. Okay, finally, there was just some, external validation by this very nice work of Malte Rosner and collaborators, and where they compared different approaches to constrained RPA for downfolding to a low energy effective subspace. It's not an exact like-for-like comparison, but they did see that that only looking at the particle hole screening channels did give some nice results compared to alternatives. So some external validation. And with that, I'd like to thank you again for listening and ask if there are any questions.
Thank you, George.
Thank you, George. Please raise your hand if you have a question for George.
So perhaps I could ask a question. I think Danish has a question. He should go first.
Yeah.
Hey, thanks for the nice talk. I have like two short questions. First, it's about so if I compare this with something like EDMFT, can you tell us something about the complexity of this approach with respect to the size of your chunk of material which you're dealing, so your small cluster, with respect to EDMFT? Have you thought about it? This would be my first. And the second question, maybe.
Okay.
Yeah, sure, please.
Let's go question by question. I assume you're talking about the extended density matrix embedding here. The advantages are, so I haven't done a side-by-side comparison, right? Mm-hmm. The advantages are that you have a finite number of analytically constructed bosons, so you don't have a continuous frequency dependence of your screened Coulomb interaction that you need to deal with. The number is finite. The number is essentially given by the square of the number of impurity orbitals. That's the number of bosons that you have to deal with. And that makes sense because it's essentially the number of particle hole excitations on the fragment of interest. So the advantage is that this directly gives you a finite quantum impurity cluster that you need to solve, but also that you only need to solve for the 1 and the 2 body reduced density matrices, the instantaneous parts of the correlation functions. You don't need to solve for the whole frequency dependence in order to do the self-consistency.
Sure, but I understand. Yeah. Okay, good. Yeah. So it really depends on the size of your, at the end of the size of your, not only about your system, but also size of the your effective bot, right? So I haven't understood this scaling.
It doesn't depend on the size of it only. So I think the problem may be conflating certain different things I touched on during the talk. If you wanted to do this exactly analogous to how you would do EDMFT, then the number of bosons is just given by the square of the number of impurity orbitals and independent of the size of the full system. Now, in the beginning, I talked about for ab initio systems, there was a way that we could further extend things if we wanted to have kind of just an uncontrolled enlargement of the bath. But in general, if you're only interested in capturing the correlated part of the instantaneous correlation functions, then this gives you a rigorous finite scaling.
Mm-hmm. And my very fast second question was the question about feedback on the single particle spectral function. So one of the effects which you get from RPA and when you get back to the spectral function are this kind of a plasmonic side peaks and all these questions, right? And I didn't really get it. Since you have the first moment, can you get this plasmonic side peaks or not?
Yeah, so what you have to do if you want to get dynamical spectral functions, because from the solver, you actually only need to get the instantaneous part of these spectral functions. You don't get the full frequency dependence. So what you're relying on is the self-consistency to get a static interaction kernel back to the RPA in order to then calculate your dynamical correlation functions from the RPA. And then you can get a lot of these kind of plasmonic long-range collective effects.
So the statement is that if you do the dynamics of the density matrix and extract the spectral function, you do get some effects of this plasmonic side peaks back.
You do get some. I'm not claiming that you will get all of the effects that if you were to do and fully converge fully dynamical EDMFT, but you will get a portion. Whether that portion is sufficient for your particular system of interest, I think would remain to be seen.
Okay, good. Thanks.
Okay, maybe we can take one last quick question since we started late a little bit. Antoine, did you have a...
Yeah, very quickly. Imagine I want to go beyond RPA and like in the GW plus EDMFT framework. Do you think this downfolding method would be a better starting point for doing EDMFT on top of the small fragment?
So when you say beyond RPA, do you mean things like including ladder diagrams?
Well, you know, when we do GW plus EDMFT, the target space, the fragment space is solved non-perturbatively, right? So the RPA approximation is done for everything else. Okay, so here your constraint is that the RPA, if I solve the fragment at the RPA level, I get the same thing than if I do a full RPA calculation from the start, if I understood correctly, right?
Yeah, but only the instantaneous part.
Only the instantaneous part.
Yeah.
But, okay, so now imagine I use this downfolding method to define an effective low energy problem for the fragment, right? And instead of using CRPA interactions, I use the MRPA or whatever you call it, interactions. Would you expect this to be more?
I would.
It's a bit of a vague question, but.
Sure. No, I mean, look, I think this really needs to have more rigorous benchmarking against CRPA to understand where it does well. I would certainly not rule it out, and I think it would be really interesting to compare. I cannot say conclusively, because I haven't done the side-by-side comparisons. I can't say conclusively one way or another, but I think it would be a really interesting direction to pursue.
Because, you know, the CRPA interactions are often too small as compared to what you would need to properly, I mean, when you compare two experiments, for example, you see that you would actually need a static value of the interaction to be slightly larger than the CRPA.
Yes. So, you know, anecdotally, it seems as though, you know, the CRPA is over screening and we have a smaller
CRPA is
screening.
definitely over screening. Yeah.
Yeah. So we tend to find that it reduces the effect of this screening. So it's, you know, seems to be pushing it in the right direction, but there hasn't been this huge comprehensive side-by-side study. One of the difficulties in doing that is because really the target spaces that we work with are often different. So the MRPA can use the target spaces of CRPA, but it doesn't have to. It can directly downfold to a local region. And I think that's one of the real strengths. So it depends whether we're comparing to doing CRPA and then truncating to all the long range or maybe even non-density density response parts. So, you know, I think MRPA can also do things that CRPA can't, which I think is one of the real strengths.